You guys want to start off by doing question 28? So the second derivative test is a version of the first derivative test where it kind of works a slightly different way. So let's talk about minimums and maximums now with this idea of concavity. Gentlemen, get focused. Alright, let's look at a standard, let's say a cubic function, like so. We clearly have a definable minimum and a definable maximum. They're both relative because they're not globals or absolutes. Right there and right there. Now, let's note a couple of things. According to the first derivative test, we can determine that this is a minimum or maximum, first derivative test, by looking at the slopes. You can see here that we have a slope that is positive on the left-hand side and a slope that is negative on the right-hand side. This indicating that you're going to have some kind of maximum. Whereas, if you want to have a minimum, you have the opposite effect. So you have a minimum, the slope on the left is negative, the slope on the right is positive. There is a similar process for this using the second derivative. Okay, the second derivative talks about concavity. So look at this picture. We can't specify exactly where the concavity changes, but we can be very general about it. In this picture, the concavity changes somewhere in between the min and the max. So I would say right about there. To the left of this value, which I'm going to call P, to the left of it, it is clearly concave down. It is opening in a downward direction. It has those properties of being concave down. To the right of P, it is clearly concave up. What the second derivative test says, rather than analyze the critical values and the places around them to determine mins and maxes, what you can do is analyze the concavity. Because take a look. For a minimum or a maximum, now instead of looking at the slopes, so this is the first derivative test, with the second derivative test, now I can just look at the concavity. If it is a critical value that also happens to be concave up, that'll make it a max. Wait, sorry. I always get this backwards. If it is concave down, it will be a max. Look at our picture to verify that fact. We can see here that this is a critical value from the first derivative test, but according to the second derivative, it has downward concavity, therefore making it a maximum. Whereas the minimum will be concave up. And again, you can see in this picture, if I label these points as A and B. So A has the property of being a critical value, but it's a critical value where it is concave down, therefore making it a maximum. B is a critical value. It has a critical value where around it is concave up, therefore making it a minimum. If you think about how to draw concavity and how to draw these critical values, this will always hold true. A place that is a critical value who has a second derivative that is positive, so it'll be concave up, will be a minimum. A place that has a critical value where it is concave down, where the second derivative is negative, that will be definition a maximum. This is referred to as a second derivative test. It's another way to determine minimums and maximums. If, say, for example, what if your first derivative is still rather nasty? Where finding the critical values is okay, but like analyzing the points is difficult. You can use a second derivative, or maybe the second derivative is just really easy to use. Like it's a nice function. Like think about it. This is a cubic function. So the first derivative is a quadratic. The second derivative is linear. That makes it much easier to work with than a quadratic does. And so therefore we can talk about its properties much faster and easier than we could by talking about the quadratics one. And again, this allows us to have fewer things we need in order to verify that it is in fact going to be positive or negative or have a min or max. Because think about it, if this situation, if it's a quadratic, think of all the things I could do. I could do the quadratic formula. I could factor. I could graph it and look for zeros. I could fundamental theorem of arithmetic. It could use one of the perfect squares formulas, where we have the difference of squares. We could use completing the square. There's all kinds of things we could use to solve this quadratic. But for the linear one, that's much easier to solve. And much faster to solve. So let's take a look at 28 in this context. So the way the second derivative works is we'll go through the same process of finding the critical values first. And then instead of using this first derivative test to determine minimum and maximum, we'll then take another derivative quickly and then use that derivative to determine if it's a maximum or a minimum. And again, so in this case, concave up, remember, it means the second derivative has a positive value for concave up. Concave down means it has a negative value. Let's look at 28. Step one of this kind of problem, we're going to take the first derivative. So, let's do that. 28. We have g of x is 3x minus x cubed plus 5. What is the first derivative, which we would call g prime of x?
3x squared minus 6. Sorry, negative 3x squared minus plus 3. I just messed that up a lot, but yeah.
You just put it in a different order than I was expecting. Okay, perfect. Sounds good. Okay, so we've got the first derivative. We're going to find the critical value, same as before. That stop's not going to change. So let's find the critical values. How do we do that? Equals 0. And? Solve. How are we going to solve that? We have negative 3x squared plus 3 equals 0.
Subtract 3 first.
Subtract 3.
Divide by 3. That's what we did.
Divide by negative 3 probably.
3, so it'd be 1.
So what's my x values?
Positive.
Very good. So that means I have an x value of 1 and an x value of negative 1. Now, instead of testing around these using the first derivative test, I'm going to use a second derivative test to determine mins and maxes. Again, same process. We're just going to use a second derivative now, and then we'll analyze our results of that second derivative instead. Now remember, these, because they're first derivative, are called critical values. When you do the second derivative, these are called points of inflection. Let's take a second derivative. What is the second derivative for this function? So g double prime of x?
Negative 6x.
Negative 6x. So what would be the points of inflection? Remember, critical values are where the derivative equals 0. Points of inflection is where the second derivative equals 0. It'd be 0. So now what I do is use the second derivative test. I need to test around 0. And again, in theory, the second derivative should be a less complex function, therefore easier to work with. So let's take a look at this second derivative. Left-hand side of 0, right-hand side of 0, I'm going to choose, and I can choose these numbers, by the way, which is convenient for the second derivative test. So I'm going to choose negative 1 and positive 1. I'm going to determine concavity. If I plug in negative 1, what happens to my function?
Positive.
It becomes positive. If I plug in positive, what happens to my function? So what's this tell us? Well, this one says left of 0 is concave up. Concave up means I'm going to have a concave up.
Min, sorry.
Going to have a minimum. That tells me at negative 1 is a minimum. At 1, it is concave down. Concave down means a negative value, which according to this would make it a maximum. So according to the second derivative test, positive 1 is a max, negative 1 is a min. And these are annoying for me sometimes because they're opposite the way I think about them. Right? The max is the negative. The min is the positive. That's because it is a second derivative. It's based on the concavity. Concavity, remember, if it is opening upwards, that's a positive number, but look at your picture, it would have a minimum. If it's opening upwards, it's got a minimum. So positive, minimum. Negative would mean it's opening downwards, maximum. Think of the picture version of these, not just the number of, it's negative, that makes it down. No. Okay? Negative does make it down, but that means that whenever we actually look at the components do it. Negative values. Let's do 29 as well. Same concept. If you haven't seen one of these before, let's talk it through, just like the last one. Let's evaluate some steps as we go. So if I'm asked to do a second derivative problem, step 1, I'm going to just give it the broad category of critical values. Because that's what we do. We take the first derivative, we say with 0, find the critical values. Okay? So step 1, we're going to find h prime, and then set equal to 0. What is h prime of x?
X squared minus 6x.
Then?
7 equals 0.
Good. So what are my critical values? How do I find them?
Factor out an x, 3x.
Factor out of 3x.
And from the figure, the records are excluded up. So
Okay.
then you have 0 and negative.
All right. Beautiful. Fantastic. Okay. So those are my critical values. Step 2, once I've got my critical values.
Second derivative.
Yep. I do second derivative. And then after you find that second derivative, we're going to find, I guess the better way to put this would be, you find critical values first. Then step 2, you find the points, point inflections, the POIs. Okay, so you find the critical values. Let's find the points of inflection. That means I need a second derivative. What is the second derivative for this function?
6x plus 6.
H double prime of x is equal to 6x plus 6.
Set equal to 0.
That equals 0 and solve.
So sorry, no, negative 3.
Negative 1. Then what do we do?
And you're going to find values around negative 1.
And what are some of the best values to use?
2, 0.
The critical values. Yes. You chose the right numbers. Just remember they happen to be the critical values. Okay, so step 1, you find the critical values. Step 2, we find the points of inflection. Step 3, what we want to do is we want to test the critical values using the second derivative.
So negative 2 would be a negative, so that would make it a maximum.
So if we look at negative 2, negative 2 times 6 would be negative 12, plus 6 would be a negative number. Yes, it would be a negative. So negative 2 would be a max.
And then 0 would be a minimum because it's positive.
Correct. I plug in 0. 0 times 6 is 0, plus 6 is a positive number. That makes it a positive over here. Positive makes it minimum. And again, to differentiate those two, think in terms of the picture. What does concave up actually look like? It looks like a U. What does concave down look like? It looks like an N. Okay? So concave down has the max, the top of the arch. Concave up has the min, bottom of the arch. Okay? And like, this is just meant to give you another way to find your points of inflection, your critical values, your relative extremity. You could still obviously use the first derivative test, but this gives you another option. Maybe your first derivative isn't something that you want to plug into. Maybe the second derivative is just really nice and easy to get. So this is just another option, another tool in your toolkit. Okay? Let's scroll down. Any question on 28 or 29 or the process, that listing of things? Remember for the last step, we'll analyze. When it comes to that second derivative, positive means a min, negative means a max. Our 4-step process using the second derivative test. Okay. Scrolling down. Identify the intervals where the function is concave up and concave down. Also identify the coordinates of any points of inflection. So this is the second derivative test. And then much the same way the first derivative test determines increasing and decreasing. We're just going to take two derivatives and solve. Ready? First one, number 30. Let's see who remembers some things. 30 says f of x is equal to x e squared.
Derivative is just x.
Nope.
What? I think
X in the square.
So f prime. So this is x times e squared, right? X is a variable. What's e squared? A constant. It's a number. It's an e. So if I take the derivative of a number times x, like let's say I have the derivative of 3x. The derivative of 3x would be 3. The derivative of 5x would be 5. The derivative of x e squared is e squared.
that order. I knew it was a constant. I was like, oh yeah. It's just X.
Okay, so it wants to find intervals of concavity, so concave up, concave down. So next step, second derivative. All right, we just said e squared is a constant. What is the derivative of the constant?
0.
0. Derivative of 5, 0, because 5 doesn't change. It's just 5. Remember, a derivative just asks the question, how is it changing? E squared is a number. It's not changing, so its derivative is 0. Okay. Identify the intervals where the function is concave up and concave down. Identify the coordinates of any points of inflection. Well, usually there's a function here. Look, there's like so there's no local max or mins, but the question didn't really ask about that, did it? It asked about concavity. So let's identify the components here. What does it mean to be concave up, according to the calculus part of this?
Concave up.
What does it mean to be concave up? It means the second derivative is positive. Will this second derivative ever be positive?
No.
So there is concave up. Never happens. What does it mean to be concave down according to the calculus of it? It means a negative second derivative. Will that ever happen?
No.
So concave down. Never occurs. Now, it's important to remember, coordinates of points of inflection, we've dealt with them in one primary way, but there is a secondary way. Same way we can deal with them when it comes to critical values. Points of inflection, we primarily talked about it when it is equal to 0. But this is equal to 0 everywhere. So let's think about it a slightly different way. Points of inflection are also places where it changes from positive to negative. Because that's what a 0 does. Is it switches your value from positive to negative. It's the intermediary in between those two. Will this ever switch from positive to negative or from negative to positive? No, because it's always 0. So in terms of points of inflection, there are none. Tricky little one, isn't it? Keep in mind, definitions are super important here, so let me put some notes up here to remind us what each of these terminologies means. Let's have a term list. Okay. Vocab day. Well, I should have had this earlier. Okay, let's talk about some terms. Okay, I'm going to stick primarily to calculus terms that we've talked about so far this year. So let's start with, critical values. We're then going to talk about increasing, decreasing, minimum, maximum. We can talk about points of inflection. We can talk about concave up and concave down. These are all calculus terms we've discussed or terms we've talked about specifically in reference to calculus topics. So you can have conversations about min and max in algebra. We have to have that conversation specifically in terms of the calculus. Okay, let's talk about each one. This basic definition should be well known for all of these. But let's go ahead and talk about each one. Critical value. This is when f prime of x equals 0 or is undefined. It is also possible mins, maxes, jumps, asymptotes. What else could it be? Endpoints, yes. Holes. These can all be critical values. So if I say the word critical value, I can be referencing any of these things and all of these things or none of these things because it may not have any critical values. If I mention holes, Endpoints, jumps, asymptotes, mins, or maxes, a part of finding them could be looking at the critical values. They work together. So if I mention an asymptote, I could talk about critical values. If I mention critical values, I could be talking about an asymptote. Or I could be talking about a minimum. Or a maximum. Alright? Increasing. So this is when f prime of x is greater than 0. Decreasing when f prime of x is less than 0. So, in terms of the definitions, increasing. This one has a positive slope. Decreasing. Negative slope. Notice, decreasing does not define how negative or how positive it is, just that it's negative or positive. So it's going down a little, it's a negative slope. Therefore, it is decreasing. Going down a lot, still a negative slope, therefore still decreasing. Important side note here. These cannot be critical values. Because by definition, critical values don't fit in that category. Neither one of them can be critical. Okay? Minimum, maximum. I think actually I'm going to move this down to the end. I'm sorry if you put these in order. I apologize. Let's do point of inflection next. Concave up, concave down, and then max. I apologize. The reason I'm doing this is so that I can use these definitions to also talk about min and maximum as well, without them being out of order. Apologies. I should have thought about that beforehand. Points of inflection. What's a point of inflection? It is when f double prime equals 0. So, places where the curvature changes. Possible curvature changes. Now, ironically, this can have some side effects because asymptotes can have curvature change depending on the type of asymptote. So this could also talk about asymptotes. Holes, usually also included in there. It's a place where the curvature has stopped working, therefore it would be a point of inflection. So this could also include places where f double prime doesn't exist. Same way that critical values include points where f prime doesn't exist. Okay, concave up. F double prime is greater than 0. Concave down. F double prime less than 0. Okay, in terms of the picture, concave up would be a general opening, a U shape. It could be an L shape, or any variations on those. Concave down, N shape, or arch shape. It could be a gamma shape. Gamma. Okay, min and max. These are the big boys. Or girls. I don't judge the gender of a min and max. It does what it wants. Big difference, apparently. Where's Michael? Alright. A minimum. We can define this in a couple ways. We can define it as the standard definition. Like f of a is less than f of x in some range. Right? Where the y value is the lowest of the values. We could define it by the first derivative test, where the slope changes from negative to positive. It could be a critical value whose second derivative is bigger than 0. A maximum. When f of a is greater than or equal to, this should be equal to, f of x, meaning it's the biggest y value. Remember, there's 3 different things to talk about here. There's f, which is the y value. There's f prime, which is the slope. There's f double prime, which is the curvature. And all 3 of these fit together in the mins and maxes. You can talk about them with the y values using f. You can talk about them using the first derivative test. Or in this case, for these ones, it goes from positive to negative. Or you can talk about it with the second derivative test. Where is a critical value whose f prime or f double prime is less than 0. So mins and maxes now have all 3 components in them. All 3 places, all 3 things. I can talk about them with the general y values from algebra. I can talk about them with the first part of calculus, the first derivative test. I can talk about the second derivative test. They all fit together. What does this mean? If I see any of these terms, I have a lot of options for how I could approach them, especially when it comes to things we're dealing with mins and maxes. We also talked about in class one day how we have different terminologies that also stand for min and max, like you could say highest and lowest. How you could say the optimization, how you could say the most versus the least. You could say the largest number and the smallest value. Like you have a lot of different versions of these things. So now that we look at 31, it states, identify the intervals where the function is concave up or concave down. Well, concave up, concave down just means where is the second derivative bigger than 0? Where is the second derivative less than 0? So that tells me I got to take a second derivative and analyze it around those points of inflection. So for 31, do we want to go through it? Okay? Awesome. Perfect. Let's do it. Okay. First step, g prime. If I want to find the second derivative, I have to first find the first derivative. Yay! Okay? Step 1. I would take its original function. We write this as x times 9 minus x squared to the 1/2 power. Step 1 is to take the derivative. I've already written it. That's a preliminary step. What are we going to do next?
X
It is a chain instead of a product.
times 1/2 9 minus x squared to the negative 1/2 times negative 2x plus 1 times 9 minus x squared to the 1/2.
Beautiful. Fantastic. Well done, man. So we did left, d right, where we have a chain. So we did the outer power first, 1/2, negative power. Then we did the derivative of the inside. Derivative of 9 is 0. Negative x squared becomes negative 2x. Plus right, d left. So right is there. D left, derivative of x is 1. This is a perfect first derivative. Well done, man. All right. We could, from here, go immediately into the second derivative. I strongly recommend simplifying first. At least a little bit. Okay, so like what things can we simplify?
X over 2 to the square root of 9 minus x squared.
I would not put it as a square root. Why would I not want it as a square root?
Shall take that derivative.
So I'm just going to take a derivative of it, so I'm going to have to immediately put it back. So what things can we simplify?
2x times 1 half.
Negative 2x times 1 half x. If I multiply those two things together, what happens? Besides the creaking of my window
Negative
here.
x squared.
Negative x squared times 9 minus x squared negative 1 half power. Okay, plus 1 times that.
Plus 9 minus x squared. 1 half.
If they've been multiplied, you would be exactly right. But since they're being added, they do not cancel. So this is beautiful. Negative x squared, parentheses 9 minus x squared to the negative 1 half power, plus 9 minus x squared to the positive 1 half power. Beautiful. Ugly in its own unique way, but beautiful in the fact that you guys get it right. Nice job.
Myself not taking the 1 half into like the 9 minus x squared.
Yeah.
That's gonna be the thing I missed. It's gonna be that.
Yep. I'm just gonna have to get you a little post-it. I'm gonna have to like smack on your chest. Don't do that. That's all I will say. I'll say don't do that. And you'll just have to be like, oh yeah, that's the square root thing. Okay? We are now in a position where it's on a pretty good step to go ahead and do the second derivative. Now there is possible more things we could rewrite this as. Like we could take that negative power and put it in the bottom instead of doing a product to a quotient. Like there's all kinds of things you could do. There's all kinds of things you could do. I will leave it at that. Okay? And that's high on the list of things I don't want to do. Is turn this into a quotient. G double prime of x. Okay, take it slow. This is a derivative that has 3 components. We have negative x squared times 9 minus x squared to the negative 1 half power. That's 2 components. Plus that second piece. Let's do it one piece at a time. Let's not miss anything. This first piece, what rules am I going to use for this piece? Chain and product. We got a product in between these two, and a chain for this particular piece. For that last piece, what are we going to do? Just a chain. Let's do it. First piece. So this is why sometimes you'll see me on the side over here, come over and be like, I'll jot down those 4 components. F prime, G, G prime. Because otherwise I'm sitting there, I'm trying to cover all of those pieces all at once. That can be really taxing on the brain. Instead of doing it here, just start writing. That way you're not trying to think, calculate, and write all at the same time. However, if you guys feel you're up to the challenge, I just want to know the 3 components. Product rule, chain inside of it.
Negative x squared times negative 1 half. Of 9 minus x squared to the negative 3 halves times negative 2x.
Oh boy. Okay?
Plus
So that is, as a reminder, this is F, G prime. So left, D right. Still finishing the product. Plus
negative 2x times 9 minus x squared to the negative 1 half.
that's right, D left. So this piece is derivative. Just that piece. So now we do plus, the second piece is derivative.
1 half 9 minus x squared to the negative 1 half.
Very good. 1 half. 9 minus x squared to the negative 1 half. Times negative 2x. The other nice part about using the side of the board, like putting it over here, we've already did that piece once. So you could just look up above and be like, oh, I did it once, so we just copy that answer down here again. That's the other advantage. Now, okay, this is where life gets real interesting. I'm supposed to find points of inflection, which means I need to tell when this thing is supposed to equal 0. Oh boy.
I feel like this is a really good question. Like going back to the degree, can you have distributed your 1 half power?
No. Remember, you cannot distribute a 1 half power as long as there is either addition or subtraction. Now, one thing that could have made this easier is we could have actually distributed the x. we could have turned this into the square root of x squared. Then multiplied it through, we would end up with the square root of 9x squared minus x to the fourth, which is just a chain. That would have made it a lot easier, rather than having a product with a chain. But you won't know that until you've tried some of these and been like, oh God, please tell me there's a better way.
I just want the 1/2 into 9 minus x squared.
I know you do.
It
I understand.
easier.
I know. And yet it's wrong.
I just obey the rules of math.
I just obey the rules of math. Ugh. Okay. Let's focus down. Let's talk simplify. Okay? There's some things that are actually pretty straightforward to simplify. And there's some things that are really not. Ready? So we have -2. Wait, hold on. Let's just one piece at a time. Negative times a negative would make this positive. X times 1/2 times -2x, that would become positive. Just to become positive x cubed.
Positive x cubed.
Hold on. Negative, 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 negative. 3 negatives makes it negative. Good. So that took care of. Okay. That piece, that piece, that piece. All right, times 9 minus x squared to -3 power. Okay, next.
Minus 2x.
Minus 2x.
Times 9 minus x squared to the -1/2.
-1/2, okay.
That's negative x minus x.
Minus x. Times
9 minus x squared to the -1/2.
All right.
Can we simplify those last two?
These last two do simplify.
Minus 3x.
So this last two, I'm going to cross those out. This becomes minus 3x times 9 minus x squared to -1/2. So I have negative x cubed times 9 minus x squared to -3/2 minus 3x times 9 minus x squared to -1/2.
Can you factor out 9 minus x squared to -1/2?
Yes, you can. That's some college algebra stuff right there. Woo! We covered it for like 2 weeks in college algebra. Let's see. I don't know how long they covered it in algebra 2. Okay, let me rewrite the problem. The problem is negative x cubed times 9 minus x squared. It scared the bejesus out of me. I was like, there's a mouse. Minus 3x times 9 minus x squared, -1/2. You too. We'll see the solution on the Google Classroom, okay? In the video.
You can really see the board in the video.
Like the screen, it's like a screen.
Okay, I might have to put a little webcam up here so they see a little bit.
Well, actually, you can factor out x and 9 minus x squared. Negative x. Right, you're right.
Here's what I'm going to do.
Can you just like make 9 minus x squared just a variable just so it's easy to add?
Wait, why can't you take negative x cubed minus
negative
3x and like move
Or you just can do
do that?
I'm going to take out a -3/2. There's a reason why. What's left behind? Well, I took a negative x out, so this becomes positive. Instead of x cubed, it becomes x squared. This entire thing disappears, so it stays just x squared. I take a negative x out, so this takes the negative out, the x out, leaving a plus and a 3. Now what happens over here? If I take a negative x cubed out,
you're left with 1/2.
we end up with that.
You
It has to do with how factoring works. So this looks nasty. Let me write a simpler version of this problem. If I have a to the -3/2 plus a to the -1/2, I can factor an a to negative 3/2 out. And what will be left behind is a 1 plus a. And you can check this by working backwards. This would become 2 over 2. When you multiply this 3, you add the powers together. Negative 3/2 plus 2/2 becomes a negative 1/2. So what I've done is accurate. It's just a difficult part of algebra that, if you don't remember, is hard. Okay? It's one of those, we literally covered it for 2 weeks in college algebra, and that was it.
I
Okay?
don't remember that.
It was in October.
Ah.
Like way back then.
Keep in mind.
Recess spring. You blocked it out. The reason why this is really, really helpful is look what happens over here now. This right-hand side simplifies very nicely.
Yes.
So we have negative x times 9 minus x squared, negative 3/2 times x squared times, so this become 27 minus 3x squared. This becomes negative 2x squared plus 27. Now we can use a fundamental theorem of arithmetic 3 times, and we have our points of inflection.
Yes.
Yes.
Points of inflection for this problem would be 0, 3, negative 3, and the positive square root of 27 over 2, the negative square root of 27 over 2.
I don't care. That's not really
Those are all the points of inflection, baby! Woo!
Is that all we have 5 or do we have that 3?
Did want to know.
Up and concave down.
Whenever I see a problem like this tells me I probably made a mistake. Meaning I either made a physical mistake or I should have done something at the beginning, like do this instead. When you see a problem that's like this and it's just like randomly 10 times longer than everything else, that's usually a clear indication sign to me of going, you done messed up. You missed something. Like,
you'll go back
these
and-
should not be this hard. And yes, then I go back through it, I'm like, where did I screw this up? Seriously. Is this pain? Like, there's no way this is fitting in this space. And they told me I'm supposed to. So this tells me I had to have made a mistake somewhere. So, keep in mind things, basic things, as we finish out today. We chose to rewrite it at the beginning. There are multiple ways to rewrite this. You have to choose a way that you think will work best. And if you can choose a way that reduces the number of rules you're going to use, especially if you're doing 2 derivatives, not just 1, 2 derivatives, which the second derivative test requires, then the more you can simplify it right at the start, later on, it grows how much work you're going to have to use, and the more you simplify, the more you save. Now compare this to this other version. The first derivative, if I did it this way instead, the first derivative would become 1/2 9x squared minus x to the 4th, the negative 1/2 times 18x minus 4x cubed. This is a simple product. I could distribute the 1/2. I then take a second derivative. It's just a product. And that's much easier to do with a product. Like, here's the thing. When I looked at it, I was like, I'm going to follow the rules. I'm confident in my ability to do this. But if you're not as confident on the algebra stuff, or you're getting to a point where you're like, what is wrong with this problem? Then you have to look back and go, okay, there had to have been a different way to do it. I didn't spot this right away. I spotted it right here. When I saw this piece, I'm like, because I looked in the head and I was like, I know this second derivative is going to be bad.
Yeah.
It's going to be nasty. As soon as I got to here, I was like, maybe I should have changed something. But, you know, I go with what you guys ask.
Don't listen to us, we're stupid.
You're not stupid. You is smart. SMRT smart.
Big time.
God.
I'll see you guys tomorrow.
Nope, we're full time.
SMRT smart. That's right.